Hey, my name is Christoph, and I'm going to present the paper Generalizing the sharp threshold phenomenon for the distributed complexity of the Lovász local lemma. And this is joint work together with Sebastian Brandt and Rozhon. For those of you who find the title a little bit off-putting, we also prepared an alternative title, namely How to Get a PODC paper by Proving that a certain set is convex. Which is rather surprising because usually you don't think about convex analysis having close relationships to distributed computing. Okay, so the paper is about the distributed Lovász local lemma. And let's start with a Sinkless Orientation problem, which can be seen as an instance of the distributed LLL. So as an input, you get a graph, and for simplicity, assume that it's d-regular. And as an output, you want to output orientation of the edges, so such that there's no sink. That is, every node should have a non-zero out degree. This, for example, is a Sinkless Orientation. And now there are two types of questions you can ask. The first one is the existential question. Does there always exist such a Sinkless Orientation? And then the second question is the constructive one. Can one efficiently find a Sinkless Orientation, let's say in a distributed setting? Let's start with the existential question. And there, the idea is to use the probabilistic method. So you choose a random orientation and you show that this random orientation is good, namely Sinkless, with strictly positive probability. What do you mean by random orientation? That is, you flip each edge independently with probability 0.5. Okay, now how can we analyze it? We define the event EI, which says that the ith node is bad, and the probability of EI is equal to 2 to the minus d. And now the simplest way one can get some result is by using a union bound. So the probability that the resulting orientation is good is the probability that you avoid all bad events simultaneously. And by union bound, this is equal is at least equal to 1 minus n times 2 to the minus d, which is strictly greater than 0 as long as d is greater than log n. Okay, but what about if d is just a constant? And in this scenario, it turns out you can use the Lovász local lemma to show that there always exists a Sinkless orientation, at least as long as d is at least 4. So what's the Lovász local lemma? There you've given some bad events, E1 up to En, and you assume that probability of EI is bounded by some number p. And now furthermore, you assume that each event depends on at most d other variants. Now that this is satisfied here in the Sinkless orientation problem, because you only depend on each other if you are neighboring. Okay. And a theorem by Erdős and Lovász says that if E times P times E plus 1 is at most 1, so E is just the Euler's number, then the probability that you avoid all bad events simultaneously is strictly greater than 0. And this condition on the left is also known as the standard LLL criterion. So in a minute, you will also encounter some other criteria. Okay, so how does it apply to the Sinkless orientation problem? There we have that P is equal to 2 to the minus D, and as D is at least 4, if you assume that D is at least 4, then we get that this criterion is satisfied, and this implies as a corollary that there exists a Sinkless orientation for every 4 regular graph. Okay, so now we have answered the existential question, and now what about the constructive question? Can one efficiently find one in a distributed setting? And there you can see or explain that this is an instance of the distributed Lovász local lemma. So what's the distributed Lovász local lemma? So there you have one node for each bad event EI. And furthermore, assume that you have independent variables x1 up to xm. And you assume that each bad event EI is a function of a subset of these random variables. And now there are two parameters. First, you assume that each xi affects at most r events. So if you associate with each random variable and hyperedge, then this means that the rank is at most r. And furthermore, you assume that each EI depends on at most d other bad events. That is, for each event EI, there are at most d other bad events with which you depend on a common random variable on. And now we're in the local model. This means that unbounded message sizes, and furthermore, it's asynchronous. And so what's the communication graph? That's simply that there's an edge between two bad events exactly if they depend on a common random variable. And now the task is to find values for the random variables x1 up to xm such that no bad event happens. And this you want to do in a distributed manner. This means at the end, each node should know the values of all the random variables it depends on. Okay, so what is known about the distributed Lovász local lemma, previous results? I don't want to go into detail, but there's the standard criterion, and there's a polylog n deterministic round complexity and randomized round complexity. So it's basically polylog n. And yes, so it's standard criterion up to some epsilon flag, so you need to have some bound on that. And there you can also think about stricter criteria. That is a criteria which is satisfied by fewer instances. That's the so-called polynomial criteria that says that if p times d to the c is less than 1 for, let's say, some large constant c. And there, in the randomized round complexity, you can a bit get faster as long as the degree is bounded. And there's an exponential criteria, and there's actually a lower bound. So for this criterion, p times 2 to the d is at most 1, which, for example, applies for the sinkless orientation blocking. You actually get the omega log n deterministic round complexity lower bound, and the omega log n randomized round complexity lower bound. And this you prove by showing that the sinkless orientation has such a lower bound. And now comes the curious thing. If it's only a little bit stricter, the criterion, namely that p times 2 to the d is strictly less than 1, then there's a sharp threshold phenomenon. And we know that round complexity drops to O log star n plus poly d, which is much faster for bounded degree graphs. And this is due to a result of Brandt, Maus, and Ito, on which we heavily build on. However, what they have only proven is if each random variable affects at most 3 bad events. And so what is our contribution? Our contribution is to lift this assumption that you don't need it anymore. Okay, so what's the algorithmic idea? And this is also from Brandt, Maus, and Ito. So they consider an arbitrary order of the random variables, x1 up to xm, and they fix the assignment one by one. And how do they do that? In such a way that a specific invariant is preserved. And of course, we need to show that there always exists such a value. And the proof that there exists always such a value relies on the convexity of a certain family of sets. And they only proved it for one set in this family, and we prove it for all of the sets. Then, so what about distributed computing? Because this seems like a sequential process. However, we can basically fix multiple random variables at once, as long as they don't depend on a common, affect a common bad event. And then you can use a coloring and iterate through the color classes. I won't go into detail there, but it's straightforward. Okay, let's do a warm-up. Let's assume that the rank is 2. That is, each xi affects exactly 2 events, such as in sinkless orientation. There you have the, so we have the criterion p times 2 to the d is less than 1. So it's not suitable for sinkless orientation, as there it's exactly equal to 1. Okay, we again do the sequential fixing as stated before. And now the question is, what value should I assign xi plus 1? And now I claim that basically you can fix xi plus 1 such that the probability that EU happens increases by at most a 2 factor, condition on the previous system, and also the probability that EB happens increases by at most a 2 factor. So this is formalized in this claim, and I won't repeat this claim, but this is all what it says. Hence, at the end, the probability of EU when we have fixed our random variables, now that is either 0 or 1, and this can be upper bounded by probability of EU at the beginning, times 2 to the d. Because each time there are at most d random variables, it depends on, and each time we fix it, the probability can increase at most by a factor of 2, and hence this is strictly less than 1 due to the criterion. Hence, none of the bad events happen at the end. Now, what about if the rank is strictly greater than 2? Does this approach generalize? And the answer is somewhat. So if you just use this approach, then basically you need to raise the 2 by r. And also you need to replace the d in the exponent by d choose r minus 1, as these are the number of random variables a particular node could depend on. Hence, you only get the result if you have a much stricter criterion as stated above. So what Brandt and Newton did, they did some different approach. So still related, but what they did, they found a clever invariant. So the idea is based on bookkeeping on edges. That is, throughout the algorithm does not only fix random variables, but it also keeps track by assigns two values on each edge. So between two events EJ and EJL, there are two values HL and ALJ. And these two values, they are non-negative, and they need to satisfy that they sum up to at most 2. And now the invariant that they define states the following. The probability that some bad event EJ happens, conditioned on all the random variables that were fixed, is bounded by the original probability times the product of L, AJL. So this seems maybe not clear at first sight. So let's do an example. So here we consider that we fix the random variables one by one. So first x1 is equal to v1, then x2 equals to v2. And at the beginning, we can set all the values on the edges equal to 1, because if you have not fixed something, then probability EJ condition on what you have fixed is just probability EJ. And hence, this is at most probability EJ times the product of some ones. However, now that we fix random variables, some bad events become more likely to happen and some less. And hence, we need to adjust these values on these edges. For example, here for the event E2, now what the invariant states is that the probability of E2, given that x1 equals v1, is at most 1.8 times 1.3 times 1 times the original probability. So these are the values on the edges. And it's because it's a product of at most d numbers, each is at most 2. You get that at the end, if you satisfy this invariant, none of the bad events happen. And here it can be that the values of the edges of a particular edge need to be updated more than once. Okay, and now there's this theorem, one can preserve the invariant. And I only give a proof sketch. So first, that was done by Brandt and Utter. There's a reduction that it suffices to prove that sets from a certain family of sets is convex. And this only takes one page and it's quite simple. So the main intuition where convexity comes into play is that, let's say you compute an expected value of some random variable, then you can see this as a convex combination of the original values weighted by the probabilities that they occur. And through this connection, there comes convexity into play. And then the second part is proof that the set is convex, or that all sets in the family of sets is convex. And there so that's our contribution. And yes, we have not found a completely easy proof, but it takes at least 10 pages or even a bit more. Okay, so I now want to focus on the second part, so prove that the set is convex. So first I need to define what set do I mean. Another connection might be not completely obvious why this is the set we care about. And to that end, we define the notion of a generator. Generator are just 6 non-negative values, and they are best visualized with this triangle where you have on each of the 3 edges, you have 2 values, and you assume that the values on one edge, they sum up to at most 2. So that's a valid generator. And each generator generates a triple, v1, v2, v3, where it's best to think about each value here corresponding to one node. And then we generate the triple by taking the products here on the close by value. So v1 is equal to a1, 2 times a1, 3, and similar for the other nodes. Now, with this notion, we can define a set of representative triples that are just all triples v1, v2, v3, such that there exists some generator, normally more than one, that generates this triple. Okay, so to make sure that the definition is clear, for example, 1, 1, 1 is in SREP, because you can set all these values here equal to 1. And also, the value 4, 0, 0 is in SREP, because you can set a12 and a13 equal to 2. And now you need to set all the other, now you need to set a21 and a31 to 0, or you can do that. And then no matter how you set a23 and a32, you get that this generator generates this triple. However, 4, 0.01, 0 is not in SREP, because if you set a12 and a13 to 2, which you need, then A21 needs to be set to 0, and similar for A31. And hence the other products will be 0, in particular 0.01. Okay. And now we define also the set of non-representable triples. So there, these are all triples in the cube 0.4 to the 3, which are not representable. And now the theorem is that S non is convex, so the set here. And so one can visualize this. Here we see this cube 0.4 to the 3, and S rep and S non are a partition of this cube. And here you can see the boundary in orange. So below that is the set S rep, and above that that's the set S non. And you can already kind of see that it is convex. But of course we formally. Okay. So, and previously for the case I equals 3, so for this particular set, actually also Brandt and Ute proved that it's convex by giving an analytical description of this boundary. But this does not generalize for higher dimensions. So what we did is the following. We used a slight variant of the following rather well-known theorem. So a set S non is a convex set if there exists a supporting hyperplane that goes through every boundary point. So you have one boundary point, and then you need to give one supporting hyperplane that is the set is on one side of this hyperplane. And why only slight variant? Because the precise theorem that we use is a locally supporting hyperplane, and then you need to additionally prove that S non is connected. So I won't define what a locally supporting hyperplane is, but one can kind of informally say that you only care about an epsilon neighborhood around this boundary point. Okay. So the first observation is that these boundary points, for which we need to show that there exists a locally supporting hyperplane, the only really interesting ones are boundary points on this orange, I don't know what this is, on this orange set, and these are all correspond to representable triples. Okay, and for each such interesting boundary point, what we do is we find 3 lines, kind of think about perturbing a generator by adding plus epsilon on one edge and minus epsilon on one edge. I won't go into detail. We find 3 lines through each interesting boundary point. And these 3 lines have the following property. All points, at least all points in a small neighborhood around this boundary point, on these lines are also representable. And it turns out that all 3 lines actually lie in the same hyperplane. And this hyperplane is actually a locally supporting hyperplane. And the proof is non-trivial, and I won't go explain it into detail, but yeah, it takes care. So the main idea is to show that not only the points on these 3 lines are representable, but also all the convex combinations, at least in an epsilon neighborhood, are representable. Okay. So what are some open problems? So for example, what happens if D is large? So if D, the degree, is not bounded, then this result kind of gets useless. And all the same is, for example, for this randomized complexity in the polynomial LLI criterion. Then are there similar thresholds in the polynomial LLI criteria regime, some sharp thresholds maybe, and then maybe some concrete applications of this regime of criteria. So it's rather restrictive. You can cook up some problems, but maybe one can find even more natural problems that solve problems one concretely cares about. All right, thanks for your attention.